So before we begin our second keynote of the day, I just have a couple of conference committee announcements that we'll quickly get through. Just another reminder that we've obtained sponsorships and partnerships with several local restaurants in the area. So there's Pimante Bros, that's on 3803 Forbes Avenue, Colombian Spot, K-Town Snack Bar, Hello Bistro, The Porch, and there's plenty of offers with all of these restaurants. Please come to the registration desk and find out more. And just help support the conference. It would help support the conference if you did. Appreciate it. Thank you. Without further ado, I'd like to introduce our second keynote speaker of the day, Dr. Karandeep Singh. Dr. Singh is the Joan and Irwin Jacob Chancellor's Endowed Chair in Digital Health Innovation and Associate Professor in Biomedical Informatics at UC San Diego, where he also serves as the Chief Health AI Officer for UC San Diego Health. In these roles, Dr. Singh leads AI initiatives within the Jacob Center and oversees AI strategy and governance for the health system, which is also going to be the subject of his talk today. He is also the maintainer and author of Tidier.jl and the associated ecosystem, and is a big Julia user. So let us give a round of applause for our speaker and welcome him to the stage.
Thanks, everyone. I'm excited to be here. This is my second JuliaCon. I started learning Julia, I think, 6 months before the 2023 JuliaCon, and attended 2 years ago. Wasn't able to make it last year, but I'm really honored to be here to talk today. There won't be actually that much about Julia. I'll share some very high-level thoughts on code tooling to do operational AI stuff and kind of what things are helpful. But I wanted to keep this focus maybe on use cases, just to give you a sense of, I hope you're at the end of this talk, you're excited about some of the challenges we have in healthcare operations and can see how Julia and tools like Julia could be useful in helping us actually improve health systems in ways that I feel like in many cases are actually solvable, tackleable, as compared to many other things that are happening that are very tough to address today. So I have one disclosure, which is that I serve on the Consumer Health Advisory Panel for Google. And a little bit about me. So I currently am the Chief Health AI Officer for UC San Diego Health. I have a leadership role in the Jacob Center for Health Innovation, which was funded by Irwin Jacobs of Qualcomm. And within that, I oversee an AI lab, which is an academic research lab within our kind of operations center. So it's essentially an academic lab charged with tackling health system operation problems where we're trying to bring the tech, but also partnership with operations to make sure that the people changes that need to happen so that the tech that we build actually is used to drive change. I'm also a kidney doctor, and although I don't work that much clinically, I work about 4 to 6 weeks a year. This week I happen to be working in the hospital, and so I have someone covering me today, so I appreciate Dr. Garimala covering me today while I am here, and I'm gonna fly back tonight so I can see my patients tomorrow. And then lastly, I'm a Julia user and developer, and as was mentioned, I have taken really dived headfirst into developing Tidier.jl, and I'll share at the very last slide some of the 3 other talks that'll be happening. So I'm not going to talk much about Tidier.jl today, but there are 3 other talks happening where you can learn more about Tidier.jl and what we're trying to achieve. But it's essentially R's tidyverse re-implemented from scratch in Julia. From scratch is maybe too strong of a word. Implemented on top of best-in-class Julia packages to bring the R syntax from tidyverse into Julia. Okay, so how did I get into healthcare operations? My dad was a computer scientist. I grew up writing software. I ended up in healthcare, and I ended up doing biomedical informatics. And I was in the midst of the pandemic studying a set of models that were actually starting to get used now in healthcare. Prior to 2020, the biggest issue in healthcare with AI was you could do it on paper, you just couldn't do it in the real world. There was no way you could actually bring those things at scale and run them within the electronic health record, which is the main kind of operating system when it comes to healthcare. So starting around 2018, 2019, a lot of the tools, kind of independent of COVID, started to become available, and many health systems now were starting to use AI tools much more broadly than they had ever used them before, with almost no, and in many cases, no independent evaluations published for any of the AI tools that we were using. So I had just kind of taken over the role of starting our AI governance back at University of Michigan prior to moving to San Diego. And one of the first models we looked to evaluate was a sepsis model developed by the electronic health record vendor. This was a model in use by hundreds of hospitals, and we were considering using it ourselves, and so we took it upon us to say we should actually try to do an independent evaluation, and we approached this in a really pragmatic way. We went to our sepsis committee. Sepsis is a body's response to a bacterial infection that makes you very sick. So we went to our sepsis committee, who are experts in this, and said, do you have a way to measure the quality of sepsis care? They said, yes, we have software we use, we have rules that we use, and we assign actually who has sepsis and who doesn't after the fact, and we assign a time zero of when that sepsis came to be, because a lot of these tools are being used in a dynamic way where they're generating predictions, let's say, every 15, 20 minutes, and so you'd want to make sure that you're not considering predictions made after the fact in actually driving care, at which point the care has already been driven by the clinician. So we found a little bit surprisingly at that time that the model that was in place in the EHR, commonly used around the country in the US, was not a great model. Later it came to, through journalistic investigation, it came to be discovered why. They were using a lot of the factors that clinicians use, they're using a lot of the evidence that clinicians essentially use as like treatments for sepsis to drive the prediction of sepsis. So it was like, doctor sees sepsis, starts treating sepsis, and now suddenly the model says, hey, I think the patient has sepsis. And that was kind of discovered as part of this evaluation process. This really got me thinking about all the things that we do in healthcare that touch technology, AI, where there's really no evaluation, and there's just a like project management style, let's implement, and not look back and see did it work. And I wanted to see if I could try to change that through my kind of hybrid operations and academic role at University of Michigan. So this caused some press. This evaluation ended up being published in a bunch of news stories, and one of them by Washington Post. It ended up influencing the FDA's guidelines and what they consider to be a medical device. Prior to our paper coming out, sepsis models were not considered in scope of the FDA. And when they issued their final guidance after our paper came out, suddenly it was now in scope of the FDA. And obviously that may change now, but that's, at least what some of the impact was with some of the work. And then actually, when the White House under the Biden administration published their AI Bill of Rights, which said, not, what are the Bill of Rights of the AI, what are the Bill of Rights of humans working with AI? So what rights should we have as humans? The first example they shared under unsafe or ineffective systems was the work that we had published on the sepsis model. So this is kind of the thing that really led me into both looking very, ground up at ways that we're using tools. That was something that, I'd written every line of R code myself to do that evaluation, all the way down to looking at how it impacts policy and how it impacts healthcare operations. And so I think something about that made me really kind of like, we need to do a lot more of this, and we need to now think, if this doesn't work, what's the alternative? How do we think about AI differently than simply as a bolt-on onto the way that we do practice medicine currently, which is not, always ideal. Okay. So health systems 101, what the heck is a health system? In every country, this term means something completely different because health systems vary a lot. In the US, there are micro health systems all over the place. So when someone says health system, they're not alluding to the US health system unless they say US health system. They're almost always alluding to the health system down the street, which may be a national chain, maybe regional, maybe local, maybe academic, maybe community. So it's really just a way of organizing the care and resources that people need when they get sick. And this is examples of some of the places where people interface with what they would consider a health system. There's a saying that if you know one health system, you know one health system. So anything you learn about one health system is not generalizable to any other health system. That's probably 80% true. I think that obviously the certain operations that every health system does are shared, but because of institutional culture and knowledge and just the ways that health systems kind of made some of the decisions they made along the way to get to where they are today, you can walk into one health system and something is totally normal, and you walk into the other health system, and that thing that one health system does would be considered completely bizarre and like like why would they ever do things that way? So I think when you're entering these systems, you have to come in with a bit of humility. You don't come in with a solution. You kind of understand what is the way that the system has evolved and how do we go about changing it, understanding what it looks like today. So I would say healthcare has two components. One is clinical care and one is operations. So clinical care is we want people to get the best diagnosis and best treatments possible. Whereas healthcare operations is that we want to make sure care is as safe and efficient as possible. This is not unlike Amazon in some ways. So Amazon, has a team that works on their recommender system and makes sure that you get the best recommendations so that you're kind of hooked and you want to use the website. And then they have probably a separate team that handles logistics and delivery, because that's another part of their core business. You might really like the product, but if it doesn't get there on time, you're not going to be happy. And so similarly, healthcare has kind of that similar breakdown between, yes, we want to get you the best possible care, and that's why people choose certain health systems, but also we need to make sure that we don't make mistakes in the process of trying to deliver the best possible care. So a lot of this talk is actually not going to focus on clinical stuff. It's going to focus on what many people view as the boring stuff, but which I find is like the cool stuff. Because this is the stuff that you actually can easily change, because a lot of this stuff has evolved in ways that is just by chance, not necessarily that that was the right way for things to evolve. I know most folks here are not in healthcare, but I'll just say it's an amazing time to be in healthcare. CAR T treatments came out a couple years ago and are basically curing cancers that were incurable. Refractory B-cell lymphomas was something that you died of, and now people get CAR T, and they're walking around, and they're totally fine, and it's essentially like they're cured. This article came out, I think, earlier this year. Kidney transplant with pig kidneys had been tried previously and always failed, so they went and they gene-edited the kidneys for the pig to make sure it didn't react against humans, and gave it to a person, and the person eventually died, but they didn't die of kidney failure. They died of other things. And so there is potentially a pathway towards completely changing the supply chain around organs, which is actually one of the biggest and most effective treatments we have today when you have organ failure, is to give you a new organ. And right now that's limited by the fact that someone has to die in many cases for some of the organs, like heart transplant, for you to be able to get an organ. And so this opens up a whole world of possibilities in healthcare that simply wasn't possible even like 5 years ago. And then of course, CRISPR-Cas and the technology around gene editing. This was the case study published in New England Journal of Medicine, where two patients with different types of disease, one of them being sickle cell disease, which people think of as incurable, had been gene edited out, and suddenly they don't have sickle cell disease anymore because they can now produce hemoglobin. So these are things that were science fiction 5 years ago, and they are like things that we can do today. So I just will say the clinical side of medicine is still super cool, but I'm gonna now use that to transition into the operations side of medicine, because we have to make sure that those treatments can be made available to people, because as we get more and more treatments, we have less and less capacity within our hospitals and our clinics to actually see the people to actually deliver those treatments to them. So healthcare is a continuum. People are at home, people are in clinic, people show up in the ER, people go to the hospital, and then after the hospital, they either go back home, or they need rehab, or they need a long-term acute care, or they need a nursing home. And I think as we think about, from a health system perspective, emergency and hospital are obviously like core to the health system. Clinic is a core part of the health system, but when any of these things has a transition state that gets backed up, it causes problems upstream. So we have problems getting people in for surgery in the hospital. You suddenly have problems getting in to see a doctor in clinic. And I think many of you who have seen kind of recently how much more challenging it is to get in to see doctors, a lot of that is a supply chain sort of issue, where we have issues on the inpatient side and that spills over and makes it issues on the outpatient side. Okay, so how does operations look? And then we'll dive into some examples and some simulation stuff. Is on a macro level, health systems are constantly balancing inpatient and outpatient capacity. Inpatient is beds in the hospital. Outpatient is being able to see people in clinic or do virtual visits. So this is constantly changing. The things I just showed you, if we have a way to suddenly cure incurable cancers, we need a heck of a lot more inpatient beds for cancer care that can deliver those treatments, because those people don't go home the next day. They have to stay for a week or two to let their immune system reconstitute. And so suddenly, that creates an inpatient problem. So if we can see them in clinic, but we can't treat them, that doesn't solve any problem. And similarly, you acquire a practice. There's all kinds of consolidations happening with mergers and acquisitions where you'll see hospital chain A and hospital chain B have merged, or we've signed a partnership with that clinic where we will exclusively provide the inpatient services for that clinic. So you can imagine that balance between inpatient and outpatient is constantly changing, and that creates problems, and essentially people have to figure out how they're actually going to deliver the care that that patient might need or that a population might need. And then as many of you guys are aware, there are deep cuts to Medicaid and Medicare coming, which are likely going to lead to rural hospital closures. And so I think either those hospitals will get bailed out by larger chains, or there will be some kind of shift that will happen. But you will no doubt see kind of impacts on operations in states that are not rural as a result of rural hospital closures. We see that even in regions where there's a hospital that's struggling an hour away, we feel that. There's a ransomware attack at a hospital, down the street, we feel that. So there's a kind of a ecosystem of healthcare in any country, state, region where you can kind of feel that at a macro level. At a micro level, health system feels like a generous term. We have a lot of individual patchwork services that are glued together that kind of individually all work well, but don't always work together well. If you look at least every system I've been in, every service is nearly at capacity. It's like you look at the hospital census dashboard, and it's almost always close to or above 100%. So I remember when I was at Michigan, seeing 103%. I'm like, wait, how is that possible? That's when they're counting how many people showed up at a football game, and I'm like, wait, they only have this many seats. How is the attendance larger than the number of seats? And it's because of this very soft, flexible capacity that health systems have that they kind of, in some cases, acquired during COVID, or in some cases had it before, where they can get a bolus of patients, and there are hallway beds. They figure out ways to care for people in ways that wasn't possible. And so one of the places this is most acute is in this concept of boarding. So a boarding patient is someone who is in the hospital, admitted to the hospital, but physically stuck in the ER because there is no bed upstairs, it might not be on upstairs, but often upstairs, that can actually take them. So just show of hands, has anyone, who's familiar with the concept of boarding? Okay, a lot of people aren't. Some people are. And I point it out because every health system capacity issue comes down to either I can't see my primary doc, or there are too many boarding patients. And this is an area where optimization, I think, is really needed. Question is it fixable? So, is boarding fixable? What I'm showing you here is data from 24 US hospitals that we published during the first week of COVID and onwards, an index to when their first COVID case was at those 24 hospitals. And this was looking at sepsis alerting patterns. So that was each of these lines here represents the proportion of patients that would have generated a sepsis alert at each of those hospitals. And you can see how after the pandemic started, the alert rates went way up, at least in theory. Not all of these resulted in actual alert. This was based on the scores, and we know what the alerting thresholds generally are. But point being, that was kind of the main finding. However, if you look in the background, you'll see that little gray area shaded in. That was actually the number of number of hospitalized patients. And you might expect that when COVID hit, the number of hospitalized patients went up, but actually it was completely the reverse. And this is why there was all these COVID conspiracy theories forming that hospitals are empty, I can't believe, doctors are complaining. And what was happening was that the reason they were empty was because all the elective surgeries got canceled. And not every bed in the hospital is allocated to someone coming from the ER. There are people who come directly from surgery and get hospitalized. And so all those had gotten canceled to create room for if we were off by one day and COVID rates were doubling in the hospital, you're off by one day, that was the difference between you can take care of someone and you are opening a field hospital. And so the margin of error was so slim that this is what many hospitals did. And so we saw that here. And you can see that this went way down. And I can guarantee to you this fixed boarding. But it also economically was not feasible. When hospitals closed their elective surgeries, they were losing millions of dollars a day There were layoffs. And so essentially, it takes required operational changes to fix boarding. And in many cases, a lot of those patients, I say elective, but elective doesn't mean like for fun. Elective means like, okay, you're not like bleeding out right now, so you can wait and we can do your surgery, but some of the elective surgeries were people who have cancer. And so it's not, elective here is a very generous term applied here. So many of those people still needed surgery. They couldn't all get out of surgery, and OR admissions make up a large part of inpatient admissions. So it is fixable, but it requires operational change. And so if you look at each phase of the health system, there are things that a health system can do based on where people are to actually improve healthcare operations. Okay, so that was a lot just background. Let's dig into actual, like, what does this look like in a real health system with real data? So this is kind of now where I'm editorializing, and this is kind of my view on health operations. There's a lot of AI stuff that every health system is doing, so I'm largely going to not talk about that stuff, because that's stuff that like is just happening, and there's no point in talking about it, at least not here. So right now, most systems can't play back what happened in like any kind of real capacity. And one of the ways that you can play back what happened is kind of by hijacking the discrete event simulation system and actually feeding in the actual patients you saw and modeling how they progress throughout your system. So this is a 6-month period, I think it's 6-7 month, at 3 of our hospitals in the UC San Diego system. And this is actually the time that people spent in days in the ER under the care of an ER physician. This is not patients who are boarding. They're still under the care of an ER physician. Actually, in some cases, it does include boarding. They're not on the floor yet. And this is the simulation time in days, populated with the actual, I call it a simulation, but this is actual patients we saw. This is accounting for, I think, 66,000 patients on this slide right here. This is the same thing, but for our inpatient services. So what can you see? If you go back, you'll see that the longest someone ever stays in the ER is like 4 days, which is a lot, but it's like an outlier. And the longer that someone stays in the hospital is like 150 days. And that's actually not even true, because I know people that stayed much, much, much longer than that. But that's just, I think, for illustration purposes, I think I may have cut it off there. But you get the point that, that's kind of the most resource that a person would use, is that much time on the inpatient side. This is just patients arriving through. And the reason it ramps up is just because we start the simulation with people who are currently in the hospital starting there, and so many of them just get discharged. And so there's a little ramp-up period before that simulation is reliable. Now if you look at resource usage, here's what the ER looks like. In a given day, an ER might be caring for 70 patients, and that same day, they might be caring for 5 patients. That's why you see this like crazy spikiness up and down. And that's because like by midnight, things are clearing out, and then, morning hits, and then suddenly it's going crazy, or in some cases, there are other periods of time. But you can see that emergency care volume is pretty unpredictable. And that's why any forecasting stuff we do, any intervention stuff we do is kind of the ebb and flow of what's happening in the area really affects it, affects the care that you give. Inpatient care volume is also pretty unpredictable. And here what you'll see, I think, is you see the week-to-week kind of trends, because there's people get discharged closer to the weekend, they're home for the weekend, we're a little bit lighter on the weekend, and then things build right back up on Monday. But you'll see that there are periods where we actually were quite light, and periods where we were actually quite heavy. And like with a delta of like 50 or 100 beds. So it's one of those things where when things are busy, it really feels like there's no way out. Because you have people, when inpatient is busy, the ER is busy. When the ER is busy, urgent care and clinics are busy because they know that people can't wait. And so there's all kinds of stuff that we can do to try to fix this kind of one piece at a time. So where would you even intervene? This is a process flow diagram that one of my colleagues, Dr. Alan Muzem and Dr. Rob Alcare put together. This is all the steps that like a patient might follow to get from where they arrive in the ER to where they go to a hospital bed and get discharged. So there's a lot of things that you could actually intervene. But one of the things that's not shown here is that set of patients who arrive not from the ER, but actually from the OR, from surgery. So one thing we have been looking at is if we look at patients who are getting surgery, is there something where we could change the day they get surgery to try to improve the balance that we have over the course of a week? So like, here's just an example. Like over the course of the week, we're really busy on Thursday, and then we kind of drop out. This is combining our 3 hospitals. At least at our main academic hospital, there's a pretty big ebb and flow. Some of the other ones are more flat, and so we've been trying to figure out how do we fix the ebb and flow at that hospital, and one of the ideas is to move some surgeries around. So if you look at operating room admissions, it's one factor driving the variability. It's probably not the major factor, it's probably not the only factor, but you can see how this is what day of the week they arrive for their elective surgery. And what you'll notice here is that very few people arrive on Friday, Saturday, and people arrive on Sunday. Of the people who arrive on these different days, which day do you think is going to have the longest length of stay? So think about that for a moment. I'm not going to do a poll, but just we'll show it and we'll talk through why. But just think through like fewer people coming on the weekend, but who is going to stay the longest on average based on which day they came in? So the thing here is that simulation is useful, but in most of the situations that I'm being asked to look at, or I'm looking at, to see if we can change things, we don't just want to simulate the current system. We want to be able to simulate an intervention. Like, what would happen if we did, move patients through a different path? And usually there are resource constraints. So I can't actually just say, take everyone who met this criteria and do that with them, because that everyone might be too big of a bucket. And so if we can't intervene on everyone, who should get the intervention? And this is where actually I think the next kind of building block comes in for health system operations is combining simulation with prediction. So what you can do is you can model patient-level risk of outcomes. And the idea is that in your simulation, as you would in real life, you try to hotspot. You take the patients who are highest risk of that outcome, and you move them. And so if you're worried about people staying the longest, you take the people with the longest predicted length of stay, and you actually move them and juggle them around, because the people with a predicted short length of stay, if your model is accurate for prediction, moving them around is not going to change much. And so you have kind of a way to balance things in your favor if you have a good prediction model and if you can do some back-of-the-envelope math. So here's the back-of-the-envelope math. This is our surgical admissions. The longest length of stay actually is people who come in Saturday, which I think is because we don't usually operate on Saturday. I mean, we do electively, but not like a scheduled case. So either these are people who are not truly elective, or they're people who need a bunch of stuff done because they're going to get surgery later in the week. So like imagine heart transplant. like we're going to bring you on the weekend so we can do a whole slew of tests on you in preparation for surgery later in the week. And we know that we have availability of beds on Saturday, so we might bring you in on Saturday. However, you can see there's not that many of them. So then you can multiply, right, your number of admissions with the predictive days on average they spend, and you can get predicted bed days. So you can see that Monday and like Wednesday are the largest contributors to bed days. People who arrive on those days eat up the most amount of bed days in the hospital. So a simple question would be, can we change that? And what would happen if we try to simulate and change that? So you start with simulation plus prediction, right? Simulate the hospital as it is now, predict prediction risk for longer length of stays, and then you simulate the intervention. And the intervention I'm going to show you an example of. This is really basic for folks who do like differential equation-based optimization problems and continuous and physics and all the SciML crowd. But this is like stuff that like hospitals don't even do, and it's basic like back-of-the-envelope math. So we take 20% of the highest risk people on Monday and just move them to Friday. Why? Well, if they're going to stay over the weekend, if they're going to stay at least 2 days, that eats up days on the weekend and frees up days on the weekday. Like, it's just simple math. And so if you were to do that, the intervention is, I'm taking the 20% highest risk patients on Monday, moving them to Friday. This is not what's going to happen. This is just simply what is the intervention. Like we could try it out. Now, to know if it works, you need to play back the simulation model, except now you bring them in on other days. And you assume that they're going to stay the same number of days. You kind of make some assumptions, and certainly, you wanted to go true discrete event simulation, you can add all kind of queues and stuff and make it fancy. But this is like the back of the envelope discrete event simulation, where we're bringing in our actual patients. And so here, we freed up 2 to 3 beds a couple days a week. And we added those beds essentially to the weekend. So you can see Monday got lighter, Tuesday got lighter, Wednesday got lighter, Thursday got lighter, Friday got busier, Saturday got a little busier, Sunday got busier. And we did this for just 20% of patients getting elective surgery, but you could do 40%, 50%, heck, you could do all of them. And you start to get the idea that like, now suddenly the equation changes. And the reason I don't like discrete event simulation like the typical way we do it in this kind of a format is because those 2 beds that are freed up, that might get other people through the system faster, or someone might schedule 2 more surgeries now and say, oh, we've got 2 beds now, let's schedule 2 more. And so I kind of think implementing queues and stuff with discrete event simulation in a hospital setting where there's such squishy capacity is like not, you can kind of naively assume, oh, suddenly people are going to get out of the hospital half a day faster, not realizing that, oh, actually we're just doing more surgeries, and we didn't solve the problem, we actually created a bigger problem, which is now we're doing even more surgeries, and we have all the same problems we had before. So, patient-level interventions can only take us so far. What I showed you is something where you would make a decision at the patient level, but one of the things that brought me to UC San Diego was an investment that Jacob's family had made in establishing a mission control. Many hospitals have this, it's like a command center, so this is not, this as a concept is not unique, but what is unique is that this is something that is really closely partnering our healthcare operations with our analytics and IT and AI teams, which means that we have a dedicated workforce co-located in one place who's actually empowered to change the time of someone's test. So, oh, your MRI's at 3 p.m.? Well, if you're gonna go home today, we can move it up, and we will trade and trade and trade, with the idea being that if we can get you out of the hospital faster, we can fill that bed faster from the ER and create a bed in the ER that someone can get seen in. And so it's almost like a F1 pit stop, but in extreme slow motion. If we can kind of get you out and reduce that turnover time, that will create 1 more slot as capacity, and that adds up over time if you can just keep doing that over not 500 laps, but over 500 patients. So one of the things that we built around the time that I was joining UC San Diego was a forecasting model for how many patients we're gonna have boarding in the hospital. And we actually give up to 10-day forecasts that go out to every leader in the system every single day. Every morning. It's a model that's freshly trained every morning, so it's a live trained econometrics model. I worked with Dr. Lily Porceltan, who has a PhD and is doing a second PhD with me. And so, we had tried econometrics models, we tried Google's time series foundation model with and without external regressors or covariates, and where we are today is a model that's substantially better in terms of error than where we were when we started. And certainly better than what we had that was built into the electronic health record. So these are things where the model is cool. The cooler thing is that we have an operational workflow where if the model says we're gonna have this many or more patients boarding tomorrow or the next 4 days, we have a set of escalations and a set of things that take place within our health system. So that I think is the cool thing is you can't be a data science team without the, in our case, chief medical officer literally driving what's gonna happen if the forecasting says it's gonna rain. We're actually gonna bring the umbrellas out. So this was cool. I spent a bunch of months working on that. We tried all kinds of different solutions. But one of the scaling issues is that what is 90% of the workflow in building a prediction model? It's not the modeling, right? It's actually getting the data, at least in the health system side. It is getting and cleaning the data is literally 90% of the work. And then the last bit is getting the right architecture and figuring out what you can do with it. And what I realized is that a lot of the reason we spend so much time getting the data is because the data is sitting in 8 different databases in all kinds of structured fields that have to be joined with missing values dealt with and all the kind of usual data science stuff that led me to develop Tidier.jl in Julia. But at NYU, they had published this paper on a model called NYU-tron, which kind of started to change the paradigm on how this works. And really, they looked at LLMs and said, we can use LLMs as predictive AI. So what you don't want to do is ask the LLM to generate a prediction. Vanderbilt tried that. I think it's dumb. It doesn't work. And every time you ask it, it will tell you something slightly different, which is good and bad, but is mostly bad in this case. But what you can do is you can take embeddings off of a large language model that runs on, let's say, someone's clinical notes, and essentially use that to train a prediction model. And what they did in NYU-tron was actually they trained a large language model from scratch on clinical documentation data at NYU, and then they supervised fine-tuned it for a whole bunch of different outcomes. And they compared that against something that was done bespoke, where the bespoke thing probably took a lot more time, although to be fair, because they were building and supervised training an LLM from scratch, they probably spent more money. But in the end, what they found is that the unstructured notes one, they can be used to train language models, but two, you can fine-tune it, and three, you actually get an AUC improvement. You get a performance improvement when you use these note-driven predictions than if you try to use the usual structured predictions. So when I came to UC San Diego, a lot of my thinking was, that's great, like that's awesome for NYU that they have the money to do that. I don't have the budget to do that, but I still want to do this. So we came up with a concept of note casting. Note casting is basically a multi-step process where you take a clinical note, run it through an LLM that has a long enough context window to summarize one note or a series of notes or the entire chart. Then you run a filter across it for anything you don't want the model to consider. That's where you handle bias. So you don't want the model to consider someone's race. Great, you run a second step that says remove any mention of that thing that you don't want it to look at. Third, you run an embedding model, and we do this in AWS, where we run a model that generates embeddings. And then all we do is, once we have that, we build a prediction model on top of that with just a two-layer neural network that can predict as many outcomes as we want in one model or separate models for separate outcomes. We're kind of still ironing out how that will play out in the real world. But the idea here is that if someone says, I have this outcome, and I want to look at the last 3 days worth of data, an hour later, we should have a prediction model for that. It shouldn't be like a 6-month process. It should just be, what things do you not want the model to consider? Great, it's done. And this matches up with clinical experience where when people are validating the model, they don't just look at the numbers, they look back in the chart and they read the text to see was the model cheating? Was there some leakage? This solves 80% of that problem, if not 90%. And so this is our note casting kind of framework. And what I say is this is inverting the thinking on predictive AI. So rather than the old way of thinking, which is you have all structured variables and you convert unstructured data into structured data and bring it into the usual thing, this says, no. We use unstructured data exclusively to predict. And if you want to consider structured data, insert that as context into the unstructured data and just completely reverse the way that we approach most prediction, which makes it scalable. And so what I care about is, can I do this at scale at a health system across dozens of outcomes? And my kind of stated goal for note casting is predict every outcome for every patient every day. So it should not be a thing where we have a patchwork of different models. We have one framework, and we can do that to do a lot of different things. And it's really just one set of calls to get those notes, and then one set of embeddings, and then everything else is separate for different outcomes. So does this work? This is preliminary unpublished data, but so far it looks like based on the current model we have in the electronic health record, we can do substantially better with just notes and basically zero mental effort. Again, you have to look at bias. You're not immune to all those issues, but essentially you've got this thing working. So you're doing simulation prediction. Do the resource constraints affect predictive AI evaluation? So think of it the other way around. Let's say I have a model that is a perfect performance. If I have resource constraints, does my model actually have perfect performance? And if you think about it hard enough, you'll arrive very quickly at the answer that no, it does not. So in other words, if you have only 3 open ICU beds, and your model says 10 patients need to go to the ICU, your realized performance is worse than what you think it is on paper. And so if you know the resource constraint, you actually can model this and say that the resource constraint not only affects the simulation, it also affects how you can evaluate the underlying prediction model. And we actually ended up writing a package in R called Model Recon for modeling with resource constraints that helps you actually calculate resource-constrained performance measures when you can apply absolute and relative constraints in like a real-world setting where you have a rough sense of, on any given day, how much openings do you have. And so whatever the model says, you only use the top X openings unless they have a higher threshold that you apply for a relative constraint. Okay, so I'm going to, I think, make one comment on measurement, and then I'll go to kind of my final slide or two. So I think the other really low-hanging fruit is that we suck at measuring things in healthcare. And we spend millions of dollars on it. And people, when they try to measure things, they try to make the measures really simple. They try to measure on very few people so that they can get it right. Or they measure it really infrequently so that by the time the measurement becomes available, it's irrelevant. All of these things are not great. And so a lot of the other work that we're doing with operations is actually automating measurement with LLMs. So this is a paper where we showed that we can get over 90% plus accuracy in extracting sepsis quality measures, which are currently done manually at most health systems using an LLM-based approach. And interestingly, when the language model is wrong, nearly half the time, it was actually the human abstractor that was wrong. So when you go back and look, you can find what the LLM found that the human missed. So this kind of really just changes the thinking around how you do measurement. And so in response to that, we've shown a similar thing for patient safety, and we've shown that we may be able to actually do a root cause analysis and present a corrective plan back to someone before they ever even look at a thing. So they're not reviewing the incident, they're reviewing the incident and the potentially corrective action that they need to take. That's all kind of through LLM-based chart review. But we think this is such a basic thing that we've built a framework internally that we call Note Reader, which is a framework for note-based question answering where it's all Llama 4 Scout driven with 10 million token context window. So we can basically send the whole chart into a thing with a set of dates. We have a batch mode where we can run it on thousands of patients. We have a single patient viewer mode. We have a mode where you can a human can actually do a human in the loop thing where they make sure the LLM is actually correct and can fine tune their prompts. We can export it as a prompt library. So this is some of the things that we're working on. So let me just close up by saying in addition to all the cool things that we're doing, we do think AI governance is important. I oversee AI governance along with two of my colleagues at UC San Diego Health. We have this is our governance process. We have a AI think shop and a health AI committee that manages AI intake and manages how we handle AI. And areas, I think, this is my summary slide of where AI can support operations: simulation, prediction, intervention, measurement, automation. I didn't touch on automation because I think a lot of people are thinking about it and there's a lot of vendors that are doing that space. But what's required to get there is having really clear operational goals. So that's a key thing. IT cannot come up with that. That's got to be operations. Operations and IT have to trust each other, and literally, it's not IT driving the show. It is operations holding IT accountable to get something done where IT thinks we can do it if we stretch. You need data science expertise, you need data science infrastructure, you need workforce training, so we're doing a bunch of workforce training on AI agents and things that individual people can do to optimize their own workflows, not necessarily system level things. And they need AI governance. And so throughout my work, I would say one of my messages is that yeah, hospitals are overwhelmed. There's so much AI slop going around that really every day I get 8 messages from vendors doing either really cool things or not really cool things, but I can't tell. Because from the initial thing, unless I am familiar with what they're doing already, you're going to be vetting a lot to figure out, is there a there for a lot of the stuff happening in AI. And so ultimately, I think we have to figure out what's working, do the back of the envelope math, figure out if you could get a perfect prediction, what could you actually do, then try to do it and get partnership with operations. And so my last slide, what is the implications for code and tooling? And this is my little mini soapbox. In general, any package I deal with, I want a higher level of abstraction also available. I want to play at the low level of abstraction, and as quickly as possible, once I grasp it, I want the higher level of abstraction. And I think many languages give you the low level of abstraction, but not the next level up. And in Julia, this is often macros. And so I would just say, macros is a really critical part of the Julia infrastructure to do higher level analysis. And I think it's super, super helpful and super critical for stuff that I do, either in Julia or in other languages where I use metaprogramming. I want deferred evaluation. I almost never want to eagerly evaluate something. I want to describe this system, have that description be an object, and then I want to execute it. R does a great job with like the recipes package and like the tidy models ecosystem where everything is deferred, and at the very end you hit run, and then it all runs. And so I think that's like a thing I love. And then I want pipeable syntax. I think chain.jl is criminally underused, and I think that has to do with the coding style of many folks who I think code. So there's a whole kind of set of folks who are happy in R, who I think look at Julia periodically, and it's the pipeable operations that really make sense from a data science mind. Very different than maybe computational modeling and other parts of the ecosystem. So just keep that in mind, that higher level abstractions for end users like me who are not mathematicians but are trying to use this to drive operations is really helpful. Stay tuned. There's a couple of Tidier.jl talks happening tomorrow and Friday. Thank you for having me. Appreciate it.
We have time for one quick question for the speaker.
First of all, very quickly, I'm just curious what the inputs were to the econometric time series forecast model of patient volume. And then also I'm wondering how your experiences in healthcare AI imply these suggestions about like pipeable syntax and deferred evaluation.
Yeah, so two separate questions. First one I would say is, I did not use a typical discrete event simulation. A typical one would be like where you use Kendall notation, and it's like MM1, where you have a defined number of like servers, you have a queue and a wait time. What I did here was actually added individual patients into the model based on their observed characteristics. And so that's why I put simulation in quotes there. And the idea would be if you're trying to optimize a process, you would replace that with a set of queues and a wait time for that process, leaving the rest of the system intact. Because I think that there's too much squishy capacity in healthcare to actually try to simulate the whole system all at once and trust the result of simulation. The second question is not so much my health experience, it's mostly being a data scientist and a data educator. I just personally find pipeable, like I think there are people who don't and there are people who love it. And in R, there are data table users and there are tidyverse users. And oftentimes that determines what type of user you are. And I would say for the tidyverse users, which I've used both, I can comfortably use either one today, but I think much more in pipeable syntax. And that's why I love things like prequel, which is essentially pipeable SQL. And so like those are the things that I view as innovative. So I think those syntax where you're defining a recipe and then you're executing the recipe is my just preferred style of working with code for data science.
With that, let's thank the speaker again.